Imagine a world where the apps you use every day, the websites you visit, that big enterprise software powering global businesses.
Hmm.
Imagine it all just appeared. Poof.
Yeah, no planning, no design, no careful building.
Sounds pretty chaotic, right? It absolutely would be. I mean, get this. A staggering 45% of digital transformation projects actually deliver lower returns than expected.
Wow, 45%, that's huge.
It is, and often it's because that really crucial foundational work, it's misunderstood and maybe mishandled. So here's a question for you listening. Have you ever wondered what really separates, a groundbreaking intuitive software solution from one that's just costly, frustrating, a total failure?
Hmm.
What's the hidden architecture behind every single digital success story?
That's such a key question because the digital world, it doesn't run on magic, does it? It runs on systems.
Right.
And learning to design them effectively, well, that starts right here. This deep dive, it's really your essential guide to understanding the systems that underpin, well, pretty much our entire technological existence these days.
Okay, let's do it. Let's unpack this blueprint of the digital world. Today, we're taking a really deep dive into the bedrock of how technology actually gets built, systems analysis and design.
S&D.
Exactly. We'll explore why this systematic approach is just absolutely crucial for any business student, any aspiring tech professional. We're drawing insights from great foundational texts like Modern Systems Analysis and Design by Valacich and George.
A classic.
It really is. And we'll dive into real-world applications, some of the challenges too. Our mission today, it's simple. Give you a shortcut to being really well informed about the core processes, the methodologies, those indispensable skills that shape the software systems of tomorrow. So whether you're prepping for your BCIS 3389 class right here at Tarleton State University's Dr. Sam Pack College of Business,
And Texans.
or, navigating the complexities of an MIS or IT program anywhere, or maybe you're just curious about how technology truly gets built, this deep dive, it's crafted specifically for you. We want to help you connect those dots between the theory and the practical career-boosting insights.
That connection is so important.
It really is. And hey, before we jump deeper into this digital blueprint, if you're already finding this deep dive valuable, do us a quick favor. Hit that like button, subscribe, maybe share it with someone else who's eager to build their future.
Yeah, your engagement really helps us bring more insider tips, more knowledge to future leaders, just like you.
Absolutely. And don't forget, we've put additional resources and insights down in the description below. They're curated specifically to help position you for a bright future in whatever career you choose.
Okay, so let's start right at the beginning. The absolute basics. What exactly is systems analysis and design? S&D.
Lay it on us.
Well, at its core, S&D is this critical, often complex organizational process. It's all about developing and then maintaining computer-based information systems.
Okay.
Think of it like this. You're meticulously examining a problem within an organization, really digging down to the root cause, and then you're crafting a precise, effective technological solution for it.
So problem first, then solution.
Exactly. And the primary purpose, it's really to make business processes not just, faster, but genuinely more efficient, more effective. And you do that by improving the design and the function of the computer systems that drive and support those processes.
Makes sense.
Now, historically, developing these systems, it was sometimes seen as more of an art, relied heavily on individual intuition, maybe a bit of guesswork.
Right, the lone genius coder myth.
Kind of, yeah. But with the rapid, just pervasive changes in IT and its widespread adoption, S&D has really evolved. It's become a highly disciplined, engineered process now.
That's a really great distinction. It's less about that single artist and, like you said, more about a carefully orchestrated team effort. It's not just about building the digital walls, right?
Not at all.
It's more like architecture. You need to understand who lives in that digital space, how they live, what their daily routines are like, and what makes that digital environment functional, beautiful, and, importantly, enduring for years to come.
That's a perfect analogy. The enduring part is key.
And central to this whole process is a figure we need to talk about, the systems analyst, a truly key player in this digital architecture.
Absolutely. The systems analyst is, you can say, the orchestrator of all these systems development activities. They act as this crucial bridge between the business needs of an organization
The business needs.
and the technological solutions that can actually meet those needs. Their core functions are incredibly diverse and vital.
Like what? What do they actually do day to day?
Well, first, they're responsible for gathering user requirements. Now that sounds simple, but it means understanding precisely what the end users need this system to do. And often, the users themselves, they don't even know how to fully articulate it.
So part mind reader.
Almost.
Yeah.
Then, they translate these often non-technical requirements into concrete technological implementations. They also have to assess the feasibility of proposed solutions.
Feasibility. How so?
Looking at multiple angles. Is it operationally viable? Can we afford it financial soundness? Do we have the tech capability? What about human factors like training, user adoption? Even legal or political concerns sometimes come into play.
Wow. Okay. It's broad.
It is. And ultimately, a good systems analyst applies technology directly to an organization's strategic goals. The aim is to maximize the benefits the company gets from its IT investments. It's not just about making something work technically, it's making it work for the business's big picture vision.
It really sounds like they're part detective, part translator, maybe part visionary, all rolled into one.
That's a good way to put it.
And what's interesting, thinking about modern SAND education, like what you'll find in a course like BCIS 3389, which really emphasizes this, is that it now places such a significant emphasis on interpersonal and planning skills, not just the tech stuff.
Oh, absolutely. That shift is critical.
It really highlights how important communication is. I mean, it's not enough to be technically brilliant, right? You have to be able to talk to people, understand those unarticulated needs, and then convey complex technical concepts in plain English.
Precisely. That translation piece is huge.
This blend of skills, the tech, the communication, the business sense, that's what makes a systems analyst truly invaluable in today's world.
Couldn't agree more.
Yeah.
So, okay, once we understand what SAND is and the pivotal role of the analyst, we can move into the guiding framework for all of this work. That's the Systems Development Lifecycle, or SDLC.
The SDLC?
Yeah. The SDLC is essentially a systematic process. You can think of it as a traditional methodology that outlines all the phases and activities involved in developing, maintaining, and enhancing software systems.
From beginning to end.
All the way from their initial inception to their eventual retirement. It provides a structured, well-organized framework, a kind of transparent roadmap for any software project, really, regardless of its size.
Like a blueprint for the building process.
Exactly. Or another analogy. Think of it like the life cycle of a living organism, from birth to death. Each system has its own unique path, its own set of developmental stages.
I like that. Organic.
It helps frame it. And it's important to understand that the SDLC, it's an organizing and guiding principle. It represents activities that must be done. But, and this is key, its exact phases and their names, well, they can certainly vary between different organizations, even different projects.
So it's not rigidly the same everywhere?
Not rigidly, no. The core idea, though, remains consistent. It's about a disciplined progression through distinct stages to build and manage a system effectively.
That's a great way to frame it, a guiding principle, not some kind of rigid dogma you have to follow exactly. Now, historically, the traditional view of the SDLC, it was often a very linear approach, wasn't it? Often called the waterfall model.
The waterfall, yes. That's the classic view.
And in that model, one phase pretty much had to be completely finished, signed off, before the next phase could even begin. It created this sequential, almost domino effect progression.
Step by step down the waterfall.
Exactly. The phases, as you see them described in sources like SAS Support or Valacich and George, typically included. First, requirements cataloging user needs. Then design, developing that detailed design document, followed by implementation, that's the actual coding. Next is verification, which is really just thorough testing of that code. And finally, maintenance for ongoing support and improvements. On paper, I mean, it looks incredibly neat, logical, like a staircase descending one step at a time.
And, that's precisely where the problems with the traditional waterfall approach often popped up. Its very rigidity became its major drawback.
How so?
Well, it treated each phase as separate and completely finished. This meant that feedback was often ignored, almost discouraged in a way. This could lock users into initial requirements that, let's be honest,
They always change.
they almost always change as the project progresses. There was also pretty limited user involvement. Their roles were narrowly defined, mostly just in that initial requirements gathering phase. And it was based on this unrealistic assumption that all needs could be perfectly specified right at the start.
Which never happens.
Never. And finally, there was often this intense focus on deadlines. Hard dates for the early phases sometimes led to rushed work, and ultimately, systems that simply didn't match what users truly needed or wanted.
And ironically, that probably ended up costing more in the long run.
Absolutely. It often increased development costs because of the extensive rework required later on. There's a paper by Diane Rhodes, for example, that highlights how an overemphasis on just documentation completion,
Checking the boxes.
exactly, checking the boxes over the actual analytical work, can lead to missed requirements and significant project delays. If your development team starts coding with incomplete or wrong requirements, failure in the testing phase becomes almost inevitable. That costs time, money, and delivers those frustrating failures we talked about right at the beginning.
Right, back to the 45% failure rate. Okay, so that waterfall model, while neat on paper, had some serious practical issues.
It did.
Which leads us to where things are now. Modern approaches to the SDLC, they've evolved quite a bit, haven't they? They acknowledge that, well, nobody ever gets it exactly right the first time.
That's the fundamental shift in thinking.
So the SDLC isn't seen as purely sequential anymore. It's understood to be much more cyclical, iterative. It allows for constant adaptation and improvement. If you picture like a circular diagram.
The feedback loops.
Yeah, you see phases like planning, analysis, design, implementation, maintenance. But crucially, there are these constant feedback loops connecting them all.
Right, so something you discover later can feed back into an earlier stage.
Exactly. A discovery made in the design phase, for instance, can feed back into analysis to refine requirements, or maybe even all the way back to planning to adjust the scope or budget. The key takeaway here is that the boundaries, the divisions between these phases, they aren't hard and fast anymore.
Much more fluid.
Phases can be combined, and a systems analyst might frequently go backward, circle back, to correct errors or omissions that are discovered later in the process. This flexibility is really what makes modern system development much more responsive and ultimately much more successful.
That adaptability is everything. So, okay, let's actually delve deeper into these core phases now, starting with planning. This phase is, well, it's absolutely critical. It sets the foundation for the entire project.
The cornerstone.
It really is. Its main objective is to identify the total information system needs of the organization, define the project's scope, its objectives, timelines, and importantly, the resources required. Think of it like meticulously mapping out an entire expedition before you even take that first step.
What are some key activities in planning?
Well, you're estimating the project size and the effort involved, creating staffing plans, establishing a detailed budget. You're also setting clear project goals, identifying specific roles and responsibilities for everyone on the team, and developing a comprehensive project plan.
The roadmap.
Exactly. Outlining tasks, schedules, assignments. This plan also includes establishing how you're going to track progress and provide oversight, how you'll manage configurations, what the training plan is, and a clear strategy for testing.
Testing strategy right from the start.
Absolutely. You need to plan for it. Often you'll conduct proof of concept activities in this phase too, basically to identify potential risks and test underlying assumptions. Asking that crucial question, can we even build this thing technically?
Okay. And how do you manage all that complexity in the plan?
Great question. We use powerful project management tools. One really invaluable one is critical path analysis, or CPA.
CPA.
CPA helps us develop and test plans for robustness. It identifies tasks that are absolutely critical for completing the project on time. Think of it like links in a chain. The critical path is the sequence of tasks that determines the shortest possible project duration.
So if anything on that path slips,
the whole project completion date slips, regardless of how fast you finish other non-critical tasks. CPA tells you exactly where to focus your attention and where resources might need to be reallocated if a critical task starts falling behind.
Got it. Focus on what truly matters for the timeline.
Precisely. Now, while CPA is great for determining the minimum project length and identifying critical tasks, its visual representation can sometimes be less immediate than, say, Gantt charts.
Ah, Gantt charts. I've seen those.
Very common. They provide a really clear visual relationship between tasks and time. They make project progress, especially for projects of medium to high complexity, immediately obvious. You often see them created using software like Microsoft Project. This is all about applying solid project management methodologies, which, by the way, directly connects to
H.Schuessler in the course, right?
Applying project management methodologies. Understanding CPA and Gantt charts seems like a really practical application for business students. Exactly. And the importance of getting this planning phase right, especially identifying that critical path, cannot be overstated. There's a famous, or perhaps infamous, example.
Oh, tell.
The Denver International Airport baggage handling system back in the 90s. It was a massive, complex, automated system. The problem was They failed to identify the baggage handling system development as being on the critical pad for the entire airport opening.
Oh,
Oh,
no.
yeah. This failure led to immense delays. The airport opening was pushed back over a year and staggering cost overruns, something like $1 million per day during the modifications. Ultimately, the initial automated system was largely scrapped. It was an unmitigated failure, highlighting just how vital thorough planning and critical path identification really are.
Wow. $1 million a day. That really hammers home how critical that initial planning is. Okay, so once you have that solid plan, hopefully avoiding Denver-level disasters, the next step is arguably where the rubber truly meets the road, understanding what you're actually supposed to be building. So let's talk about the analysis phase, and specifically the often tricky world of requirements gathering. The objective here is clear. Comprehensively analyze all the requirements. That means gathering detailed information from stakeholders, truly understanding user needs, and then clearly defining the system's functionality, its constraints, its specifications.
It's the deep dive into the what.
Exactly. And it's really important to emphasize, as you mentioned earlier, that these requirements ideally are developed by the end user, or at least in very close collaboration with them, not solely by the developer.
Absolute critical. This ensures the system truly meets the business needs and isn't just some technical exercise in coding that looks cool but doesn't actually solve the problem.
Right. So how do you actually capture these requirements, especially when users might struggle to articulate them?
That's where the analyst's skill and specific tools come in. That detective work we talked about. One of the most common visual modeling techniques we use is use cases.
Use cases.
Yep.
Invented by Ivor Jacobson, right?
That's the one. Use cases are fantastic because they capture functional requirements in non-technical terms, basically, in plain English. They describe the specific business rules being implemented, making them accessible and understandable for both technical folks and business stakeholders.
That communication bridge again.
Exactly. And this is a core skill you'll definitely hone in your BCIS 3389 coursework, learning to translate real-world business scenarios into these clear functional diagrams. It directly relates to KO4, utilizing standard UML diagrams, and SO1, implementing use case diagrams from business cases.
So use cases are one tool. What else?
Well, there's also the Rational Unified Process, or RUP, which is now distributed by IBM. RUP isn't just a technique, it's more of an adaptable process framework for iterative software development. It defines clear roles, the who does what, work products, the what gets produced, and tasks, the how specific development goals are achieved across different disciplines like business modeling and requirements gathering.
More structured then.
A bit more structured, yes, but adaptable. We also often see things like report mockups. These are frequently done in simple tools, even Excel sometimes, just to provide visual representations of what reports should look like. They can be really helpful and are often appended to the formal requirements documents.
Makes sense. Seeing is believing.
It often helps clarify things. Now, one of the biggest challenges in this phase is ensuring that the requirements aren't just, a wish list from users.
Yeah, I want a button that does everything.
Pretty much. They need to be thoroughly analyzed needs tied back to actual business value. And that's why having a strong validation plan for the testing team right from this stage is so crucial. It ensures that what eventually gets built is actually what's truly needed and specified. Without that validation link, you're essentially building blind.
Okay. So analysis nails down the what. From that clear understanding, we then transition into the design phase. And here, the objective shifts to creating the actual software blueprint based on those requirements you just gathered. This phase details the system's architecture, the database structure, the user interface, and other critical technical specifications. It really defines what you are going to build in technical terms, not necessarily every single line of code, but the overall structure and components.
Exactly. This is where the logical specifications of the system, the what, start to transform into the physical design, the technology-specific details that the programmers will actually use to build the system.
What are some key outputs or elements of this design phase?
You'll see things like functional hierarchy diagrams, showing how different parts of the system relate, detailed screen layout diagrams, tables outlining specific business rules, business process diagrams, often using UML activity diagrams to map out workflow.
Activity diagrams. That connects to the course outcomes too, right?
It does. KO4, again, using standard UML and specifically SO2, implementing activity diagrams to model those business processes from case studies. You also develop pseudocode to outline programming logic and, crucially, complete entity relationship diagrams, or ERDs.
For the database.
Precisely. Often expressed using UML class diagrams. along with a full data dictionary. This defines the database structure, the tables, the fields, the relationships. That's another key skill, SO3, implementing those class diagrams for database design.
So lots of diagrams and specifications.
A lot of detailed planning before coding starts. An important step here is getting approval from the system architect, especially if the new system needs to integrate with existing older legacy systems. You have to make sure the changes won't inadvertently break something else already running.
That integration piece sounds tricky.
It can be very tricky. And this phase is also where the detailed test plans are often developed, building on the strategy from the planning phase. The level of review and detail in these test plans usually depends on the project's inherent risk. Higher risk, more rigorous test planning.
Makes sense. Plan the tests before you build the thing you need to test. Okay, once that detailed blueprint, the design, is complete and approved, we move into actually building it. The implementation or coding phase, and then the acceptance phase.
Right. So in the implementation part, this is where the developers finally get to write the actual code, following those detailed design specifications.
Usually board time.
Lots of keyword time. But it's more than just typing. It involves setting up a proper development environment, using sophisticated editors that help with things like syntax checking, and crucially, employing industry-standard version control systems.
Like Git.
Exactly, like Git. These systems are essential for managing changes collaboratively, keeping track of every code iteration, and allowing teams to work together effectively without overwriting each other's work. This is also where initial testing happens at the developer level, often called unit testing. Individual developers ensure their specific piece of code runs without errors, doesn't throw warnings, and produces the expected results for simple inputs.
So developers test their own stuff first.
Ideally, yes. And then comes the more formal acceptance phase, which is all about rigorous testing by others. This evaluates the software's overall functionality, its performance under load, its reliability, to ensure it truly meets the customer expectations and those original requirements we gathered way back in analysis.
And who does this acceptance testing?
Well, ideally, user acceptance testing, or UAT, is conducted by an independent test group, not the developers who built it.
Why independent?
Fresh eyes. They bring a different perspective and aren't biased by having written the code. This independent team typically develops its own comprehensive independent test plan. This plan includes detailed test data, specific test cases, and various scenarios designed to exercise all the different logical paths within the system.
Trying to break it, essentially.
In a controlled way, yes. The results of this rigorous process lead to the validation of the code, verifying that the system behaves as expected. Correct inputs produce the correct outputs. And a critical part of this, especially when changes are made, is regression testing.
Regression testing? What's that?
Regression testing ensures that any new changes, new features, or bug fixes haven't inadvertently broken existing functionality somewhere else in the system.
The ripple effect.
Exactly. You need to make sure that development outputs still match production outputs where they're expected to. Imagine changing one part of a really complex machine, like swapping out a gear, and not checking if another, seemingly unrelated part suddenly stopped working because of it. That's what regression testing prevents. It's crucial for maintaining stability.
Got it. Test, validate, make sure you didn't break anything else.
Okay, so after the system has been thoroughly built, tested, and accepted, we finally get to the deployment phase.
The rollout.
Yeah. This is all about the logistics of actually delivering the final product to the customer, getting it out there. It involves activities like installing the software, configuring it in its live production environment.
Flipping the switch. Pretty much. But it's often more involved than that. This phase might also include comprehensive training for the end users to make sure they can actually use the new system effectively. And importantly, it often involves transitioning the responsibility for future development, ongoing support, bug fixes to a dedicated support staff or maintenance team. Ensures the system has a clear path forward once it's live. It's the grand unveiling, but yeah, with a lot of careful orchestration behind the scenes.
And as we know, a system's life doesn't just end at deployment. It then enters the crucial and often longest maintenance phase.
Right. Keeping it running.
Exactly. The main objective here is ongoing support. That includes fixing bugs that crop up, tuning performance if things slow down, and implementing updates or enhancements over time. It's all about ensuring the software remains current, reliable, and continues to align with the business's evolving requirements.
So it's not static even after launch.
Far from it. But here's something often overlooked. The maintenance phase isn't just about fixing problems. It's actually a goldmine for understanding how people are really using the system and identifying evolving user needs. Think of it as constant real-time feedback flowing back.
So it informs future development, too.
It absolutely should. Key activities during this phase involve developing and updating user guides and training materials to reflect any new functionality or changes.
Yeah.
It also addresses any modifications needed to standard operating procedures or maintenance routines. And critically, every single production run, especially for batch systems, needs to be verified. Nothing is assumed to work perfectly forever.
Diligence is key.
It is. And to manage all the ongoing feedback, the bug reports, the enhancement ideas, a robust change request system is usually put into place. This allows users and stakeholders to formally request changes or report issues. If your change request system isn't robust and well managed, you're essentially flying blind when it comes to improving the system, rather than evolving it strategically based on actual use and feedback.
Makes sense. You need a formal way to capture those ideas and problems. Okay, and then sadly, every system eventually reaches its final stage, the retirement phase.
The end of the line.
This is when the system reaches its end of life. Maybe it's outdated, maybe the technology is obsolete, maybe it's being completely replaced by a newer, better system. It's removed from use.
Sunsetted, as they sometimes say.
Exactly. The process here typically requires notifying users well in advance, providing clear explanations about the new systems they'll be transitioning to, if any. And it often involves careful tracking to ensure all users have successfully moved off the old system and data has been migrated or archived appropriately.
Yeah, you can't just turn it off one day without warning. For example, maybe you're migrating from an older, less secure file transfer protocol, FTP, system to a more secure SFTP. That requires careful notification, training on the new process, and monitoring to ensure no critical data transfers are missed or left vulnerable on the old system. It's really about the dignified and safe decommissioning of a digital workhorse.
A fitting end. Okay, so we've walked through the traditional SDLC phase by phase. But as you said earlier, the digital world is far from static. Things change fast.
Incredibly fast.
Yeah.
Which brings us squarely into the realm of modern methodologies. These approaches truly embrace flexibility, iteration, and that idea of continuous improvement we touched on.
And the big one everyone talks about is Agile.
Indeed. The rise of Agile methodologies really came about precisely to address those rigidities and shortcomings we discussed with the traditional waterfall SDLC, especially in today's really dynamic business environments where requirements can, and often do, change frequently, even mid-project.
So what is Agile, fundamentally?
Fundamentally, Agile is a modern approach to project management and software development. It's renowned for its flexibility, its highly collaborative approach, and its continuous adaptation to evolving requirements. But more than just a set of practices, it's really a mindset that prioritizes customer satisfaction and continuous improvement above rigidly following a predefined plan.
A mindset shift. I like that. It's about being responsive, not just following steps blindly.
That's the core idea. Be responsive to change.
Okay, so if we compare Agile directly to that traditional SDLC waterfall model, what are the key differences that really stand out?
There are several quite stark differences. Let's look at the approach. Agile is iterative and incremental. You build a little, get feedback, refine it, build the next little bit. Traditional SDLC is linear and sequential. Step 1, then step 2, then step 3.
Waterfall versus cycles.
Exactly. Then flexibility. Agile thrives on adaptability. Changing requirements are expected and welcomed. SDLC typically follows a fixed, predefined plan, making changes difficult and costly later on.
How work is structured?
Agile divides work into short, time-boxed iterations, usually called sprints, typically lasting a few weeks. SDLC has distinct, longer sequential phases like analysis, design, etc.
What about getting feedback?
Big difference here. Feedback in Agile is frequent and continuous, often daily, involving stakeholders directly. In SDLC, feedback is typically gathered only at the end of each major phase, sometimes months apart.
Collaboration must be different too.
Hugely different. Collaboration in Agile promotes close, daily interaction among cross-functional teams and very active customer involvement throughout the entire process. SDLC collaboration is often more structured, more formal, and limited to specific points in the process.
And when do you get working software?
Good question. With Agile's delivery time, you often get a minimum viable product, MVP, a basic working version delivered much earlier in the process, allowing for real user feedback sooner. SDLC typically delivers the full, completed product only at the very end.
What about documentation? Waterfall loved documentation.
It did. Agile values working software over comprehensive documentation. That doesn't mean no documentation, but it's streamlined and focused on what's essential. SDLC emphasizes detailed documentation at each and every phase, which can slow things down.
And finally, handling risk.
Risk management in Agile is ongoing. Risks are identified and addressed throughout the development process, offering more flexibility to adapt. SDLC tends to address risks primarily in the initial planning phase, with less flexibility for changes later if new risks emerge.
Those differences really paint a clear picture. It highlights why Agile offers such powerful benefits, especially today. That adaptability to change seems critical.
It is, especially in dynamic business environments. It enables faster time to market because you're delivering functional increments quickly. It fosters that genuine customer collaboration, ensuring continuous feedback keeps the product aligned with actual expectations.
Right, building what they really need.
And it promotes continuous improvement through mechanisms like sprint retrospectives, where the team reflects on what went well and what could be better. Ultimately, all this often leads to higher product quality through frequent testing and things like code reviews baked into the process.
Yeah.
I remember one project I was on, we simply moved to doing daily stand-up meetings, just 15 minutes each morning.
Just that one change.
Just that.
Yeah.
And the sheer shift in transparency, in team communication, in catching problems early, it just transformed our team dynamic almost overnight. It seems like a small change, but the impact was absolutely profound. It really speaks to the power of Agile principles in action.
That's a fantastic real-world example. It really does speak to the power of those sometimes subtle shifts in process and communication. But you mentioned earlier there's a crucial distinction within these modern methodologies that often gets confused. Incremental versus iterative development.
Ah, yes. This is so important and often misunderstood. Dr. Alistair Cockburn, who's a key figure in the Agile movement, really emphasizes this. These terms, incremental and iterative, they have distinct purposes and very significant management implications. Teams can run into a lot of trouble if they confuse the two, or maybe only do one without the other.
Okay, so let's break them down. What is incremental development?
So incremental development is primarily a staging and scheduling strategy. Think of it like building a house piece by piece, but maybe focusing on completing entire rooms or sections. You complete the foundation, then maybe the first floor framing and walls, then the second floor, integrating as you go.
Adding on piece by piece.
Exactly. It's about developing various parts of the system at different times or rates, and then integrating them as they are completed. Cockburn uses an analogy of a digital cube. Top layer is UI, middle is middleware, bottom is backend. In incremental development, you might build a fully functional vertical slice, a piece of the UI, its matching middleware logic, and its backend database components and get that working. Then you add on to that with more functional slices in the next increment. The goal is to deliver working, add-on pieces of functionality over time.
Okay, that's incremental adding pieces. So what is iterative development then?
Iterative development is fundamentally different. It's a rework scheduling strategy. Time is deliberately set aside to revise and improve parts of the system that have already been built, even if they were built incrementally.
So it's about redoing and refining.
Precisely. It's crucial because our initial assumptions about requirements, about the user interface design, about the technology choices, the architecture, maybe even the algorithms, they're often wrong, or at least not entirely optimized the first time around.
Like performance issues.
Performance under load is a classic example. Initial guesses often prove incorrect once you hit real-world usage, potentially requiring significant architectural revisions. That's iteration, going back and fixing or improving what you already built based on new information or feedback.
How does that work in practice? How do you know when to iterate?
Well, Cockburn illustrates this really well with what he calls the validation V diagram. The idea is, after you've coded something, maybe an increment, you don't just check it off and move on. You test it, yes, but then you examine it from several different standpoints.
Examine how.
You ask critical questions. Was this the right thing to develop in the first place? Did we build the right feature? Do the users genuinely like the way it works? Is it intuitive? And crucially, does it perform well enough under real-world conditions? This examine step is absolutely fundamental to iteration. It ensures we're building the right product, the best product we can, not just a product that technically functions.
Okay, so you build a bit, then you examine it critically. How do you manage that rework?
There are generally two main strategies for handling the rework identified during examination. One approach is to try and develop the system as well as possible up front, making your best guesses, assuming only minor changes will be needed later. This can work for simpler things, but it's risky for complex systems.
What's the other way?
The other strategy, often favored in iterative approaches, is to develop the absolute least amount possible before sending it out for evaluation or examination. This minimizes wasted effort if it turns out major changes are required based on feedback.
Build small, test often, change easily.
You got it. There's a great illustrative anecdote adapted by Jeff Patton about Leonardo da Vinci painting the Mona Lisa iteratively, instead of disappearing for years and coming back with the finished masterpiece.
The big reveal.
Right. Imagine instead Leonardo shows some initial sketches to his patron early on. The patron looks and says, no, she can't be looking to the right like that. She absolutely has to be looking to the left. Because it's just an early sketch. Charcoal on paper.
Easy change.
Super easy change. Then maybe Leonardo adds some basic color washes, comes back and says, okay, by cost, I'm about 1/3 done now. What do you think? The patron might look and suggest, make her head look a bit more balanced, maybe adjust the background. Again, changes are relatively easy because significant effort hasn't been locked in yet. This iterative refinement, driven by continuous feedback, allows for significant adjustments early on, preventing those really costly, painful reworks much later in the process.
That Mona Lisa analogy really makes the difference clear. Incremental adds pieces, iterative refines them, and it sounds like you really need both for success.
Absolutely. Both are needed for truly successful projects. If you only increment without iterating, without that examine and refine step, you risk just diligently delivering what people do not want, as Cockburn aptly warns. You just keep adding features onto a potentially flawed foundation or a poorly designed core.
Building the wrong thing faster.
Exactly. That's why a composite strategy, blending the two, is so powerful. You can structure your project with incremental deliveries, but within each increment, you build in time for those iterative cycles of examination and rework before integrating that piece into the larger system. This flexible approach allows you to map tangible milestones to your project plan, clearly showing when each incremental part is developed, examined, potentially reworked, integrated, and maybe even shipped to early users. It helps avoid those frustrating, costly failures we started with.
It really sounds like the key is that built-in feedback loop and the willingness to change based on it.
That's the heart of it, and we've seen this play out in real-world projects, both successes and failures, based on how well they understood and applied these concepts.
Got any examples?
Sure. Cockburn mentions Project Baker. This project unfortunately confused iterative with incremental. They set up their work in a pipeline with month-long cycles for different stages like requirements, design, coding, testing. But then management gave instructions that requirements and design could change at any time. Chaos. Total pandemonium. Programmers were trying to code a system based on designs that the designers had already changed because the requirements writers had already revised the requirements again. The testers never got anything that actually fit together coherently.
Right.
It was a classic failure of uncontrolled, poorly managed iteration within a rigid, pipelined, incremental approach. They were iterating without control and incrementing without stability.
Okay, so that's confusing the two. What about doing one without the other?
Right. Then there was Project Laddie. This was explicitly an Agile project using 2-week iterations, or sprints. They focused on developing user stories to completion within each sprint. But there was never any time factored in within those 2 weeks to actually show the customer what was being designed or built before it was considered done.
No feedback during the sprint.
Effectively, no meaningful feedback loop during the sprint that could lead to changes within that same sprint. So customers felt pressured, like they had to get things right the first time when they defined the user stories. This completely violated the spirit of Agile, where that continuous feedback and adaptation is paramount. They were incrementing quickly, but without the crucial iterative refinement based on early feedback.
Wow. So even calling it Agile doesn't guarantee you're doing it right. Sounds like a textbook case of, we meant well, but the whiteboard forgot to talk to the code editor.
Exactly. Process over purpose. But thankfully, there are success stories too, like Project Winifred. This was a challenging project. Fixed price, fixed scope, fixed time. They structured it with 3-month incremental delivery cycles.
Okay, larger increments.
Yes, but crucially, within each 3-month cycle, the development teams showed their ongoing work to real users at least twice, typically around the 6-week mark and again around 8 weeks.
Getting feedback mid-increment.
Precisely. At that first viewing, maybe when 60–80% of the increment's functionality was complete, users had the right to change anything. They could even say, I know that's what I said I wanted back in requirements, but now that I actually see it working, it's really not what I need at all.
That takes courage from the team to allow that.
It does, but it's essential. By the second viewing, closer to the end of the increment, maybe 90–95% complete, only fine-tuning and fixing egregious mistakes could be corrected. This blended approach, clear increments with built-in iteration and user feedback, successfully delivered what the users actually wanted and needed. It led to a successful, long-lived system, really demonstrating the power of integrating both incremental and iterative development thoughtfully.
Those stories truly highlight the difference between just following steps and actually understanding the principles. Okay, building on Agile, let's get even more specific. Can you touch on some popular Agile frameworks people might encounter?
Absolutely. There are several, but two very common ones are Extreme Programming, or XP, and Scrum.
XP, what's that about?
XP is often described as an evolutionary approach to software development. It's characterized by really short development cycles, incremental planning, and a very strong focus on automated tests. Interestingly, these tests are often written collaboratively by both programmers and customers to ensure they reflect real business needs.
Customers writing tests.
Or at least defining the acceptance criteria for them, yeah. XP also often involves practices like pair programming, where two developers work together at a single workstation. One drives, writes code, while the other navigates, reviews things ahead. In XP, coding and testing are very tightly integrated into a continuous flow.
Intense, but sounds effective. What about Scrum? That one seems really popular.
Scrum is probably the most widely adopted Agile framework today. It's designed specifically for speed and managing complex projects, often aiming for multiple functional product releases. The primary unit of work in Scrum is the sprint.
The 2 to 4 week cycle you mentioned.
Exactly, typically 2 to 4 weeks. Each sprint is treated like a complete mini project in itself, aiming to deliver a potentially shippable increment of the product.
How does a sprint work?
Each sprint kicks off with a sprint planning meeting, usually up to 8 hours for a month-long sprint. Here, the team decides what work can be delivered by the end of the sprint, selected from the product backlog, and how they'll accomplish that work, creating a sprint backlog of tasks.
Okay, plan the sprint.
Then what? Then, during the sprint, there's a daily stand-up, or daily scrum, a strict 15-minute meeting each day where team members quickly share what they did yesterday, what they'll do today, and any impediments they're facing. It keeps everyone synchronized.
Quick check-in.
Very quick, very focused. Once the sprint work is complete, there are two important events. First, a sprint review, typically up to 4 hours, where the team demonstrates the work they completed to stakeholders and gets feedback. Second, a sprint retrospective, usually up to 3 hours, where the team reflects internally on the sprint itself, what went well, what didn't, and how they can improve their process for the next sprint.
Inspect and adapt.
That's the mantra. Scrum also defines key artifacts. The product backlog, which is the master-ordered list of everything known to be needed in the product. The sprint backlog, which is the subset of product backlog items selected for a specific sprint, plus the plan for delivering them. And the increment, which is the sum of all the completed product backlog items from a sprint, plus the value of increments from previous sprints that should be potentially shippable.
So Scrum provides a clear framework, roles, events, artifacts for implementing that Agile mindset. Understanding these frameworks like XP and Scrum seems like it provides really practical application of those project management and systems development principles we've been discussing.
Definitely.
They give structure to the flexibility.
Okay, shifting gears slightly. We've talked a lot about processes and methodologies. Let's talk about the people involved, specifically the essential skills for systems analysts. This role sounds incredibly demanding, truly multifaceted. It seems like it requires a whole spectrum of abilities. It really does. You absolutely need a strong technical foundation. An analyst should have a good understanding of different types of information systems, things like decision support systems, DSS, executive information systems, EIS, maybe even expert systems or geographic information systems, GIS, depending on the context. They need to understand the technology landscape.
Makes sense. Got to know the tools.
But equally, if not arguably more important sometimes, are strong communication skills. We keep coming back to this, but it's vital. The ability to effectively bridge the gap between business terms and technology terms is paramount. Many professionals, regardless of their experience level, genuinely struggle to communicate effectively about systems, especially when talking across different functional departments.
The classic IT versus the business divide.
Exactly. A systems analyst must be able to translate complex technical jargon into understandable business language for stakeholders, and just as importantly, translate fuzzy business needs into clear, actionable technical requirements for the developers. This directly links to the writing outcome, W01, in your course, demonstrating that ability to communicate SA&D concepts effectively in writing, choosing the right tools, applying them, and conveying findings to others. It's about avoiding those critical communication pitfalls.
Communication is key. What else?
Well, Closely related are crucial interpersonal skills. Just being able to work well with others, build rapport, manage conflict sometimes. Analysts often act as internal consultants, helping users navigate difficult choices, differentiate between what they want versus what they truly need from a system.
Managing expectations.
Managing expectations, balancing trade-offs between features, cost, and time, and helping determine that crucial return on investment, ROI. You also need critical thinking and flexibility. Maintaining an objective viewpoint, being open to multiple possibilities and solutions, not getting locked into one idea too early. It's about applying abstract models and concepts to messy real-world problems.
Seeing the forest and the trees.
Precisely. And related to that is effective problem solving. Knowing what information is actually relevant to the problem at hand, validating the integrity of data you're given, formulating and testing hypotheses about potential solutions. A Harvard Business Review study actually highlighted that even data-savvy professionals sometimes lack these core problem-solving skills when faced with data.
Interesting. Data literacy isn't enough.
It's not just about reading the data. It's about knowing what questions to ask and how to interpret the answers critically. All these skills really underscore the importance of hands-on experience working through real-world scenarios, case studies, practical application, exactly like the project-oriented cases and projects emphasized in BCIS 3389. Theory is great, but applying it is where the learning really sticks.
Absolutely. And wearing all these skill hats means the systems analyst plays several key roles within an organization, doesn't it?
They certainly do. We touched on some already, but let's highlight them. First, they definitely act as a consultant, helping end users navigate those tricky trade-offs, managing expectations around costs and time, and crucially, helping the business determine the potential return on investment for proposed system solutions.
The internal advisor.
Right. They're also often the go-to technical expert, or at least a key technical liaison. They need to ensure that any solutions being considered, even if they involve external consultants or vendors, truly align with the organization's broader technical strategy and objectives. They maintain that internal technical congruency.
Keeping everyone on the same technical page.
Exactly. The analyst is also frequently a powerful change agent. New systems or significant modifications inevitably bring change to how people work, and change can be hard. The analyst often becomes the proponent of this change, using their reasoning, justification skills, and communication abilities to ease the impact on end-user processes, their access to information, and their training needs. Using techniques like prototyping can really help. Here, it provides a safe, low-risk way for users to evaluate proposed changes and provide feedback before anything disruptive is rolled out.
Making change less scary.
Trying to, yes. And finally, systems analysts serve as evaluators. They need to provide accurate assessments of development activities, progress, and outcomes, which is essential for effective project planning and budgeting going forward. This requires objectivity, even if it means critically examining past decisions or projects to learn from failures. You mentioned the Standish Group study earlier.
Yeah, less than a third of projects being fully successful.
Right. That statistic really underscores the vital need for analysts and organizations to learn from what goes wrong, not just sweep failures under the rug, in order to improve future system implementations. Being an objective evaluator is key to that learning process.
Consultant, technical expert, change agent, evaluator definitely requires a broad skill set. Now, looking at the bigger picture of modern software development, it's clear there are some significant major challenges that organizations and analysts are grappling with today.
Oh, absolutely. The landscape is constantly shifting. What do you see as the common thread weaving through many of these hurdles? Because I think there might be one.
That's a good question. Maybe. It's often not the technology itself, but the human element, the culture, the communication, how we think about problems.
I think you've hit on something crucial there. Let's look at some specifics. One of the most pressing is just keeping pace with innovation. Technology changes at this blinding speed, right? Organizations are often struggling with clunky, outdated legacy systems. These aren't just inefficient. They're often major security risks and huge roadblocks to doing anything new or innovative.
Technical debt.
Massive technical debt. And remember that McKinsey stat 45% of digital transformation projects failing to meet expected returns. I think a lot of that comes down to a fundamental misunderstanding of the difference between simple optimization and true transformation. Are you just doing the same old things a bit faster, or are you fundamentally rethinking how you operate using new digital capabilities? Many companies, frankly, aim too low.
So managing legacy systems and aiming for real transformation, not just tweaks. What else?
No. Another huge one is cultural change. Rodolfo Carmona, over at Three Pillar Global, put it really well. He said the biggest shift needed for successful digital transformation isn't the technology itself, but how teams actually work together. Breaking down those traditional silos between departments, fostering a culture that embraces rapid adaptation, creativity, collaboration, all focused on enhancing the user experience. It's absolutely paramount, but, and this is key, it has to be driven from the top down and permeate the entire organization. Without that supportive culture, even the best technology implementations will likely fall short.
The org chart getting in the way of the flow chart?
You could say that.
Yeah.
Then there's the ever-growing complexity of data privacy. The regulatory landscape is just a minefield. You've got GDPR, CCPA in California, state-level laws popping up everywhere, and the penalties for non-compliance are strict. As Javier Trevino points out, systems absolutely must be designed with adaptability in mind to cope with these constantly evolving rules. Plus, you have industry-specific regulations like HIPAA for healthcare or PCI DSS for payments that add another layer of complexity. Just staying compliant is a continuous battle.
A moving target.
Absolutely. And related to that, we can't ignore the pervasive threat of cybersecurity. Attacks are getting more sophisticated, fueled by the expansion of IoT devices, massive data streaming, cloud-native applications, the prevalence of remote work creating more endpoints. We're even seeing AI-powered hacking tools emerging. Managing the sheer influx of data from things like 5G and Wi-Fi 6 also presents security challenges. It's a constant arms race.
Seems like security needs to be baked in from the start, not bolted on later.
Essential. And speaking of AI and automation themselves present challenges. It's not just about if you automate, but when and how. How do you use AI effectively to power human augmentation, making people better at their jobs rather than just replacing them? Navigating the complexities of things like test automation requires real strategy and skilled resources. It's not magic, it requires careful planning.
And making sure people can actually use these AI tools.
That leads straight into data literacy. It's not enough to have data scientists building complex AI models. You need to equip the end users, the business decision makers, to actually understand and act on the insights these systems provide. Often this involves implementing user-friendly, self-serve business intelligence, BI tools, and intuitive data visualizations. But fundamentally, as that HBR study suggested, it comes back to fostering those core problem-solving skills alongside the technical literacy.
Making data accessible and actionable for everyone.
Exactly. Then there's the challenge of cross-platform functionality. Users now expect a seamless, unified experience, whether they're on their phone, tablet, desktop, smart TV, Roku, Apple TV, Fire TV, Xbox, you name it. Delivering that consistent functionality and aesthetic across all these different devices, despite their varying underlying architectures, is a huge technical and design challenge.
Keeping the experience smooth everywhere.
Smooth and consistent. And of course, there's always budgeting. Especially in uncertain economic times, IT departments are often asked to do more with less. This requires constantly reevaluating business cases for projects, maybe reallocating resources from lower priority areas, and really sharpening the focus on initiatives that drive genuine digital innovation and business value.
Prioritization is key.
Absolutely.
Yeah.
And underpinning almost all of these challenges is the persistent talent shortage. The competition for highly specialized skills, data science, AML, cybersecurity, is incredibly fierce. Organizations need to look beyond just the hard technical skills and also focus on crucial soft skills like empathy, communication, adaptability. And as IBM research highlights, there's a growing need to proactively upskill and reskill existing workforces to build a future-proof team capable of navigating this complex landscape. These challenges are all interconnected, and tackling them requires a really holistic strategic approach, often putting that skilled systems analyst right at the center of it all.
Wow, that's quite a list of challenges. Keeping pace, culture, privacy, security, AI, data literacy, cross-platform, budget, talent. It's a complex world out there for software development. And what really stands out to me listening to all those challenges is how often the user or the customer experience is implicitly or explicitly at the center of the problem or the solution.
Excellent point.
That brings us directly to user-centered design, UCD, which feels less like a nice-to-have these days and more like a strategic imperative, wouldn't you say?
Absolutely, more than ever. Why is it so essential now? Well, the consequences of poor user experience are just too high. It leads directly to low adoption rates for new software. High churn rates. Think about mobile apps. Wikipedia cites data suggesting nearly 25% of users abandon an app after just one use if the experience is bad.
One chance to make a first impression.
Pretty much. Poor UX also leads to increased customer support costs because people can't figure things out, and ultimately it often requires expensive redesigns and rework down the line. Getting it wrong is costly.
So what is user-centered design fundamentally?
UCD is all about creating products, software, websites, apps that actively prioritize the user's needs, their behaviors, their expectations throughout the entire development cycle. It doesn't rely on guesswork or assumptions about what users want. Instead, it's driven by continuous user feedback, direct user testing, and iterative improvements, all aimed at building software that is not just functional, but genuinely intuitive and efficient to use.
What are the core principles?
Key principles include involving users actively at every stage of the process, from requirements gathering through testing, making usability meaning easy to learn, efficient to use, forgiving of errors the primary goal, embracing iterative design, using those feedback loops constantly to refine the product, and increasingly a strong focus on accessibility and inclusivity, ensuring the product can be used effectively by people with diverse abilities and backgrounds.
The business impact of doing UCD well.
It's significant. First, it provides a clear competitive advantage. Users naturally gravitate towards platforms and tools that are effortless and pleasant to use. Think about the apps you prefer on your phone. Second, it leads directly to increased adoption and engagement. People use software they like. Third, cost and time efficiency. As mentioned, fixing a usability problem after development could be exponentially so let's say up to 100 times more expensive than addressing it during the design phase with early prototypes and testing.
Wow, 100 times. That's huge.
It really is. UCD also leads to improved brand reputation. Companies, known for great user experiences, build strong customer loyalty. And interestingly, it can even positively impact SEO and discoverability, because search engines tend to rank user-friendly, accessible websites higher. It's really about building something that not only functions flawlessly, but genuinely delights the people who actually use it every day.
So how does the UCD process typically work? What are the steps?
It usually follows a cycle. Step 1 is understanding users. This involves research, things like surveys, user interviews, analyzing usage data, analytics, observing users interacting with existing systems. From this research, you create user personas, detailed profiles of your target users to keep your needs front and center.
Okay, know your user.
Step 2 is wireframing and prototyping. Based on the user understanding, designers create visual maps of the user journey and low-fidelity wireframes or interactive prototypes. Tools like Figma, Adobe XD, or Sketch are common here. This allows the team and users to visualize the flow and layout before any code is written, catching potential usability issues extremely early and cheaply.
Test the blueprint before building the house.
Exactly. Step 3 is testing and feedback. This is where those prototypes or early versions get put in front of real users. Techniques include A/B testing, different design options, using heat maps to see where users click, conducting formal usability lab sessions, or simply observing users trying to complete tasks. The goal is to identify pain points, confusion, and areas for improvement.
Watch where they struggle.
Precisely. And that leads directly to step 4, iteration and refinement. Based on the feedback gathered during testing, the design is tweaked, optimized, and improved. Then you might go back to prototyping or testing again. It's a continuous cycle of designing, testing, and refining until the usability goals are met. Key factors throughout this process include ensuring accessibility standards are met, optimizing navigation and overall usability, paying attention to visual design and branding, and making decisions based on data and user feedback, not just opinions.
Design, test, learn, repeat. It sounds like a very practical, user-focused way to build better software.
It is, and it avoids so many problems down the road.
Okay. As you can probably hear listening to this, everything we've discussed today, the SDLC phases, modern methodologies like Agile, the tools, the skills, the challenges, the focus on users, it all aligns perfectly with what you'll be covering in a course like BCIS 3389 here at Tarleton.
Definitely hits all the key points.
The course description itself says it's a study of the systematic analysis, design, and implementation of software systems, with special emphasis on the processes and skills used in the first 4 stages of the system development lifecycle. We've explored those stages in depth. It mentions traditional and current methodologies, including computer-aided analysis and design tools will be considered. We've hit waterfall, agile, UML diagrams, and it notes topics will be approached through project-oriented cases and projects, which integrate theory and practical application. This whole deep dive is designed to prepare you for exactly that kind of integration.
And let's quickly connect this back directly to those specific learning outcomes for BCIS 3389, framing them as really actionable insights for your future career growth. Looking at your knowledge outcomes.
Okay.
KO1, basic economic models. When we talked about feasibility studies, ROI calculations, budgeting challenges, that's applying economic models directly to system decisions, it's critical for making sound business cases.
Right, the why behind the project.
KO2, basic organizational models. Understanding those cultural change challenges we discussed, the importance of effective team collaboration, the different roles analysts play, and how systems need to support strategic organizational plans, that's applying organizational models.
Seeing the system within the business context.
KO3, basic systems concepts. Grasping the SDLC phases, the components that make up an information system, and crucially, that distinction between incremental and iterative development, knowing when to add on versus when to refine, that's fundamental systems thinking.
The building blocks.
KO4, standard UML diagrams. Learning to actually use case diagrams for requirements, activity diagrams for business processes, and class diagrams for database structures. These aren't just academic exercises. They are practical, standard tools for analysis, design, and clear communication in the real world.
Tools to trade.
KO5, project management methodologies. Being able to utilize tools like critical path analysis and Gantt charts gives you the power to plan effectively, manage risks proactively, and ensure projects stay on track, a skill universally valued in absolutely any professional field.
Project management is everywhere.
Then your skills outcomes, SO, are about putting that knowledge into practice. SO1, implement use case diagrams from business cases. This means you can take a real-world business scenario and translate it directly into clear functional requirements using a standard notation. Invaluable. SO2, implement activity diagrams from business cases. You'll be able to visually model complex business processes, making it easier to spot inefficiencies, bottlenecks, and opportunities for improvement. SO3, implement class diagrams from business cases. This teaches you the fundamental skill of designing robust, well-structured database schemas, which is foundational for almost any IT or data-related role.
Building the actual models.
Exactly. And finally, your writing outcomes, WO, are about tying it all together through communication. WO1, communicate S&D concepts in written format. The ability to clearly articulate why you chose certain analysis tools, how you applied them to a specific case, and then effectively communicate your findings and recommendations to a third party, maybe management, maybe clients. The skill is absolutely paramount for effective project leadership and for avoiding those critical, costly communication pitfalls throughout your career. These aren't just course objectives. They are practical tools and insights designed to give you a real edge.
And while they might not be explicitly listed as values outcomes in the syllabus, it feels like the course and this whole field inherently fosters crucial values too. Things like critical thinking, adaptability, problem solving, and definitely the importance of ethical considerations like data privacy and cybersecurity when you're designing these systems. These seem absolutely crucial for lifelong learning and career growth, especially within the context of the Dr. Sam Pack College of Business and its focus on responsible leadership.
Well said. Those underlying values are incredibly important in shaping responsible and effective professionals.
So let's try to wrap this up. What does all of this mean for you, the listener? Today, we've really taken a comprehensive journey, a deep dive, through the intricate world of systems analysis and design.
We covered a lot of ground.
We really did. We've explored the systematic approach of the SDLC, both traditional and modern. We looked at the agility and flexibility of modern methodologies like Agile, Scrum, and XP. And we highlighted the critical skills, both technical and interpersonal, that you need to master. From understanding user requirements all the way through managing complex project timelines and dealing with modern challenges, hopefully, you now have a much clearer picture of how digital solutions actually come to life, and more importantly, how you can be a part of shaping that future.
And remember that bold question we started with.
Yeah.
About the difference between a groundbreaking success and a frustrating failure in software. It really isn't magic. It's the diligent, intelligent, user-focused application of these systems analysis and design principles we've discussed today. It's about building solutions that are not just technically functional, but are truly user-centered, adaptable, and strategically aligned with business goals. Exactly the kind of groundbreaking solutions we all want to build and use.
Well put. We really hope this deep dive has sparked your curiosity and equipped you with some valuable insights you can take forward. If you found this discussion helpful, please show your support, like this deep dive, subscribe to our channel so you don't miss future ones, and maybe share it with your peers or colleagues who might also benefit.
And don't forget, we've gathered even more curated resources for you, links, articles, further reading down in the description below. Definitely check those out.
Please do.
So here's a final thought to leave you with. Behind every single tap, every swipe, every click you make on your devices, there's a system that someone, somewhere, designed. The real question is, what kind of system will you design? What problems will you choose to solve? And what kind of future will you help build with these skills?
Until next time, from the Dr. Sam Pack College of Business, keep building the future one process at a time.